Welcome back to 8701. So we continue our discussion of nuclear physics, and in this lecture, we talk about the nuclear force. Now, in the last lecture, we saw that nuclei bound together, and we were able to calculate using an empirical model the binding energy of various nuclei. Now, the question remains, what is actually binding those nuclei together? If you remember, I mean, in the first weeks and months of this lecture, we looked and discussed various interactions between elementary particles. We saw the electromagnetic interactions, the weak interaction, and the strong interactions. But there was no discussion of the nuclear interaction or the nuclear force. Now, what is this? So we have seen that the strong force acts between quarks in hadrons. For example, we have discussed at length the pion, which is made up of an up quark and a down quark, and those are held together or bound together via the strong force. And we looked also at the structure of a proton and the structure of a neutron. Now, the nuclear force is the residual interaction between the quarks localized in different hadrons. So the interactions between, for example, this up quark here and the down quark here in a different nuclei. You can already understand that it will be difficult to have a full understanding of the nuclear force. Why? Because there's many quarks involved, and there's many protons and nucleons involved in this process. So what we find is later that we can describe this using a mean field approach, a mean field of forces between the particles involved. So what is the experimental status? Our understanding of the nuclear force is based on various kinds of experimental information. The first comes from nucleon, proton, neutron, and proton-neutron scattering experiments. And some of those experiments have the benefit of using spin-polarized projectiles. For example, a polarized electron being used to probe the structure of a nucleus. Nuclear binding energies, we've seen those again, and the precision measurement of masses, they give us insight, especially useful for the light nuclei. And the nuclear structure information, such as energies, energy levels, spin, parities, magnetic and quadrupole moments, again, especially of the light nuclei. And there's many more to be named in more detail, but conceptually, those are the three kind of pieces of information we have. Those experimental results, they indicate that the nuclear force depends on the distance between the interacting nucleons. This is the radial part. How far apart are those nucleons? And also the spin and angular momentum of the interacting nucleons. There seems to be a spin orbit and also a tensor part when it comes to the nuclear force. It is also interesting to note, and we'll talk about this more, is that there doesn't seem to be any indication that the nuclear force depends on the type of nucleon, whether or not it's a proton or a neutron in the interaction. So there's charge independence. So looking at the radial part of this, the nuclear force is short range, which implies it vanishes for distances longer than about 2 femtometers. So it basically vanishes in this area here. And the nuclear force is strongly repulsive for distances shorter than about 0.5 in this area femtometers. You can understand the repulsiveness by the fact that you cannot really push or press an existing nucleon further than its actual radius. You cannot compress them further. This is also kind of apparent in the liquid drop model, where we discussed, a volume term, and the volume cannot be compressed further. On the other hand, you saw that there's short range distance, in fact, because we find this linearity with the mass number in the binding energies. Right, so here are the arguments. The binding energies per nuclear, which is roughly constant, indicates that the nucleons in nuclei interact only in their immediate neighbors. Right? Otherwise, you would have an A squared term or an A times A minus 1 term in there. And then the measurement of distances between the nuclei at which nuclear reactions start to occur. Those are in the order of 1 to 2 femtometers larger than the corresponding radii. The nuclear densities, which are only slightly smaller than the nuclear densities, indicating very dense packing. So again, they are already very densely packed. You cannot push them much further. On the spin orbit force, here that's an area where we could go into much more detail, but for this introductory class we will not. The scattering of spin polarized nucleons or other spin nuclide particles allows us to understand that the nuclear force has a component which depends on the spin and the angular momentum of the interaction nuclei. Here's a fun fact. So the charge independent on nuclear forces, meaning that the nuclear force doesn't really depend on whether or not there's protons or neutrons. And you can, I could ask you, would you have expected this? Would you have expected that there is a dependence on the charge? And the answer should have been no, because we just learned that the nuclear force is a remnant of the strong interaction. The strong interaction doesn't know about electric charges. So the answer needs to be yes. The charge independence of nuclear force implies that the electromagnetic effects are eliminated in the scattering, meaning when you measure aspects of the nuclear force, you have to be aware of the fact that there is electromagnetic interactions, and you have to kind of try to get them out. And that can be done by, for example, comparing scatterings of protons and protons, protons and neutrons, neutrons and neutrons. You do a comparison carefully and subtract out the electromagnetic effect, and you see that the force is indeed independent of the charge. We can make use of this. So there's a lot of information behind or experimental techniques which can make use of the fact that nuclear forces are charge independent. What you can, for example, do is study so-called mirror nucleus. Those are the ones where basically revert the N and the Z for the same A. So they're basically mirrors of themselves in terms of mirroring the protons and the neutrons. Examples are helium-3 and tritium, for example. Those then allow you to study in detail those effects. So this heavy mirror nuclei, the breaking effect, the effect breaking charge independence of the nuclear force are strong, and the similar does not hold. Good. One example where you can study this is, for example, one of those mirrors is radioactive or an unstable nuclei. You can study the properties of this unstable nuclei by looking in detail at the mirrored nucleus. So that's a rather common and interesting way to study radioactive nuclei, where you cannot just simply take them, excite them, and study their properties. Simply decay too fast in some cases. Here's a table where you see this effect. You see the comparison between the nuclei, this mirror nuclei here. There's 4 pairs, and you see that the binding energy, the net binding energy after removing the Coulomb term, is very much the same between those groups, those mirrored groups of nuclei. And this table here, or this diagram, shows you excitation energies for 2 mirrored nuclei, and you see that the energy levels are pretty much on par. Without going into any detail, they're on par between those 2 mirrored nuclei.